Welcome back. We're going to talk about Markov processes. Last time we talked about the Fibonacci series. Let me briefly review what that was about. So the Fibonacci series is a sequence of numbers. You start with two ones and then add them to get 2, and then 1 plus 2 is 3 and 2 plus 3 is 5 and so on. Every number is the sum of the previous two numbers. That is to say, if you write these numbers fk, it says fk plus 1 is equal to fk plus 2. And we put this into a matrix like this, and we write fk plus 1 fk is equal to, well, when you multiply this out, you get the sum of these two, which is fk plus 2 and fk plus 1. And so it gives you the next term in the series, and you keep applying this matrix to generate all of the rest of the Fibonacci numbers. And so we saw that what we're ultimately doing is we're computing a to the k times this original vector 1, 1, where this is the matrix A. And we know how to compute powers of matrices. We have to find the eigenvalues and eigenvectors. And it turns out that for A, the eigenvalues are 1 plus radical 5 over 2 and 1 minus radical 5 over 2. And by plugging that in and doing a calculation, we found a closed form for the kth Fibonacci number. It turns out that fk is 1 over radical 5 times 1 plus radical 5 over 2 to the k minus 1 minus radical 5 over 2 to the k. Okay, so this is all discussed in the book on page 255 and 256. I went through that kind of quickly because I did it in class last time, but I wanted to briefly say what it's about. And you should all read this section if you haven't already, and stare at this formula for a minute. It's quite amazing, actually, that this is a closed formula for the kth Fibonacci number. In particular, if you look at this formula, it doesn't even look like it's giving you an integer. It has all these radical 5s in it, not to mention the 2's in the denominator. But in fact, this does miraculously come out to be the kth Fibonacci number. Okay, well, the Fibonacci numbers illustrate the basic idea behind Markov processes. Before we get into that, let me remind you of the technique that we're using here, and that is, how do we compute powers of a matrix? And actually, what we want to do is compute powers of a matrix applied to some fixed vector u. And we've seen this before. What you do is you diagonalize. You write A is equal to S D S inverse, where S is the eigenvectors of the matrix A put in as columns. And then you compute that A to the k applied to u is equal to S times D to the k applied to S inverse u. Okay, so this is the key formula. And observe that this vector here is fixed. You just compute S inverse u once, and then this is the thing that's varying with k. You get lambda 1 to the k, lambda n to the k. And then S, of course, at the end you multiply it by that once. And one of the important things is going to be what happens as k goes to infinity. And what's important is the size of the lambda i's. And the important case in the case of Markov processes is going to be the following. Suppose that lambda 1, for the sake of discussion, was greater than or equal to 1, and suppose that all of the others were strictly less than 1. Well, then what happens is this term dominates, and all of these powers go to 0. And what you conclude is that as k goes to infinity, you a to the k, u, approaches some multiple of the first eigenvector. All the other eigenvectors go away, and you approach this eigenvector and out towards infinity. You're going further and further out, but the direction that you're going is in the direction of the largest eigenvalue. Okay, now we're going to go on and talk about Markov processes. There's a good example in the book, simple as it may be, which is California. And the claim is that every year, 1/10 of the people that live outside of California move in, and every year 2/10 of the people living inside California move out. Well, okay, I know that's ridiculous, but let's go with it. And so let's suppose that we started off with Y0 people outside California and Z0 people in. Then after 1 year, what's the story? Well, the number of people outside has gone down by 1/10. So the number of people outside is going to have a term like this. And there's also this term is giving us plus 0.2 times Z0. And what's happening to the number of people inside? Well, 1/10 of the people outside moved in, and 2/10 of the people inside moved out, leaving 0.8. Okay, so that's a pair of linked linear equations. And we're interested in this is a 1 here. We're interested in repeating this process. And so just as in the case of the Fibonacci numbers, obviously the thing that you wind up doing is having to compute powers of this matrix, 0.9, 0.2, 0.1, and 0.8. And the first thing to observe is that the sum in each of the columns, the sum in each column is equal to 1. And that corresponds to the fact that there's conservation of people. The total number of people balances and the total number of people moving out and moving in, and that accounts for this property. And there's another property of this matrix. Well, all of its entries are positive, and we're going to see, in fact, that all of its entries are positive even when you take powers. So the other fact is that all entries in A to the K are positive. And these are basically the two defining properties of a Markov matrix or Markov process. All right, so let's compute these powers. So this is our matrix A. And if you compute the eigenvalues by taking the determinant of A minus lambda and so on, you find that it has two eigenvalues. Lambda 1 is equal to 1, and lambda 2 is equal to 0.7. And the lambda 1, the one eigenvector is 2/3, 1/3, and the other one is 1/3 minus 1/3. All right, and so now when we compute what happens after k steps, you get yk zk. That's going to be equal to this matrix S, which is to say 2/3, 1/3, 1/3 minus 1/3. Times 1 to the k, 0.7 to the k. That's the d to the k term. And then the inverse turns out to be 1, 1, 1 minus 2. And that's all applied to our fixed y0, z0. Okay. So as I said, this is this fixed vector. We can write it as y0 plus z0, y0 minus 2z0. And whatever y0 and z0 are, I don't care at the moment. And then we're going to be applying this to it. And when you work this out, you see what you get is exactly y0 plus z0 times this eigenvector 2/3, 1/3. and well, that's times 1 to the k, and then the other term becomes y naught minus 2 z naught 0.7 to the k times this other eigenvector 1/3 minus 1/3. Okay, so it's the general form of this expression that's important as opposed to the actual numbers which are occurring. So the key point is that this is the eigenvector v1, and this is the eigenvector v, I'll call it v.7 for the eigenvector with eigenvalue 0.7. And in front of this eigenvector is a 1 to the k, and over here is a 0.7 to the k. And then here and here are some more or less arbitrary starting conditions. These could be anything depending on what y naught and z naught are. And as I said a moment ago, the key thing is as k goes to infinity, well, this term just goes away. And what you wind up with is you're just approaching this y naught, you approach y naught plus z naught, some fixed constant, times this 2/3, 1/3. And notice that because the eigenvalue is 1, you're not going out to infinity, you're actually just approaching this very value, this finite multiple times the eigenvector. All right, so that illustrates all of the key ideas in Markov processes, in a Markov process or a Markov matrix. So A is a what it means for A to be a Markov matrix is it has the following properties that we just saw in the examples. Each column adds to 1. And 1 is an eigenvalue. And all of the other eigenvalues, their absolute value is less than or equal to 1. And so note that what happens is, just like in the previous example, if V1 is the one eigenvector, well, this is what's called a steady state, which is to say if you start at some multiple of V1, and you apply as many powers of A to the K to it as you want, you don't go anywhere. This thing is just fixed. And all of the others approach one eigenvectors, which is to say these other eigenvectors, if you have some other v lambda, well, when you apply lots of powers to k to it, it's approaching 0 because the absolute value of lambda is less than 1. So that's the typical classical behavior of a Markov process as realized by a Markov matrix. Well, let me just mention one fact about these Markov matrices, which is that if you have a matrix A where the columns add to 1, that alone, that very fact tells you that 1 is an eigenvalue. It's kind of neat. Why is that? Well, if you take this matrix and you subtract 1 from each of the diagonal entries, then you've subtracted 1 in each column exactly once. So now the sum of each column, the sum along each column is 0. And so what that means is if you add the rows, row 1 plus ... row n, what do you get? Well, the first coordinate is the sum of the first coordinates, which is 0, and so on. You get the 0 vector. and that's a linear relation. So the rows are linearly dependent, and therefore the determinant of this matrix is 0, and that's exactly what it means for 1 to be an eigenvalue. So that's that's the fact that 1 is an eigenvalue is an elementary consequence of the columns adding up to 1. Okay, well, let's talk about more general difference equations, not just Markov processes. So a general difference equation is the following. You start with some fixed vector u0, and then you get a new vector by applying a to it, and you get a sequence of vectors u2, ... where u1 is a to the k applied to u0. And, well, I should have said a applied to uk is uk plus 1, which means that the way you get the kth vector, is you apply a k times to u0. And I've discussed this several times already, so I'll say very quickly, how do you solve this? How do you figure this out? Well, you write a is equal to S d S inverse, where S is the matrix consisting of the eigenvectors. And if the eigenvectors are v1 through vn with corresponding eigenvalues lambda 1 through lambda n, what do you find? You find that uk is going to be of the following form. It's some constant times a power of lambda 1 times v1 plus another constant times the power of lambda 2 times v2 plus and so on. This is what we've seen in a couple of special cases, and exactly the same thing works in general, where these constants c1 through cn depend on the initial conditions, the initial vector u0. So never mind exactly what that is at the moment. This is qualitatively what happens, and I want to look at this and figure out what the behavior of these vectors is. And it's clear that the crucial thing is the size of these lambda i's, which is to say, if the absolute value of lambda I is less than 1, or equal to 1, or greater than 1, that's going to be 3 different kinds of behavior. So if you look at lambda 1, for example, if it's bigger than 1 in absolute value, this term is going to go to infinity. If it's equal to 1, it's just going to sit there, and if it's less than 1, it's going to go to 0. So looking at this equation, c1 lambda 1 to the k v1 plus so on and so forth, we see that these vectors are stable if the absolute value of lambda I is less than 1 for all I. And we see that the behavior is unstable if some lambda j has absolute value bigger than 1. Okay, and what does that mean? If it's stable, then uk approaches this, just goes smack down to the 0 vector as k goes to infinity, right? Because if this number is less than 1, this is going to 0. And whatever your initial conditions are, you're going to be going towards 0. Whereas in the unstable case, that is to say, let's say that lambda j is bigger than 1 in absolute value, well, then lambda j to the k in absolute value is going to infinity. And so the solutions go to infinity, at least most of them do. There might be a very small number which don't, but almost all of them go to infinity. So that's the unstable situation. So this is the first case of stability. We're going to see several different examples of this kind of behavior. And it's really shows you that everything is controlled by the size of the eigenvalues. All right, I think that's a good place to stop. I will see you in class.